The AI infrastructure crunch. Can the world power the AI boom? Every AI breakthrough you hear about has a physical cost. Behind every new model release, every generative tool, every automated workflow, there is something far less visible: electricity, chips, water, land, transmission lines, cooling systems. The AI revolution does not run on code alone. It runs on infrastructure. And that raises a critical question. Can the world actually power the AI boom? This is not about whether AI is useful. It is about whether the physical systems underneath it can scale fast enough to support it. Because intelligence at scale requires energy at scale. Over the past few years, artificial intelligence systems have grown dramatically in size and complexity. Training state-of-the-art models now requires thousands of specialized processors running in parallel inside massive data centers. These facilities are not small server rooms. They are industrial-scale operations, often consuming as much electricity as a small city. And that demand is rising. Each generation of AI models typically requires more computing power than the last. Not just marginally more, sometimes multiples more. Larger datasets, longer training cycles, higher precision, more redundancy. But computing power does not exist in abstraction. It requires advanced semiconductors, the kind produced in only a few highly specialized fabrication facilities worldwide. It requires data centers, large buildings packed with racks of high-density servers. It requires reliable electricity, around the clock, without interruption. And increasingly, it requires water, for cooling systems that keep these processors from overheating. This is where the infrastructure crunch begins. Let's start with electricity. AI data centers consume enormous amounts of power. A single high-performance AI training cluster can draw tens of megawatts. At scale, large facilities can reach hundreds of megawatts. To put that in perspective, 1 gigawatt is roughly the output of a large power plant. Some of the largest hyperscale data centers approach that scale when aggregated. Now multiply that by dozens of facilities globally. The question is not whether grids can supply electricity today. The question is whether they can supply rapidly growing demand tomorrow, while also powering electrified transport, heating systems, industrial production, and renewable energy transitions. Power grids were designed around relatively predictable demand growth. AI introduces a new variable: concentrated, high-density, rapidly scaling load. That changes grid planning. Utilities must consider transmission capacity, transformer upgrades, substation expansion, long-term generation contracts. And building new power generation, whether renewable, nuclear, or fossil, takes years. The AI industry is moving faster than traditional energy infrastructure. That mismatch creates pressure. Next, semiconductors. Advanced AI systems rely on specialized high-performance chips designed specifically for parallel computation. These chips are expensive. They are power-hungry. And they are manufactured in a small number of advanced fabrication facilities. Scaling AI means scaling advanced chip production. But building new semiconductor fabrication plants requires tens of billions of dollars, years of construction, highly specialized equipment, highly trained engineers, reliable access to ultra-pure water, stable electricity supply. Even with aggressive investment programs underway in the United States, Europe, and Asia, advanced chip manufacturing capacity cannot expand overnight. AI demand competes with consumer electronics, automotive systems, telecommunications equipment, defense applications. There is no separate AI-only supply chain. It shares infrastructure with the rest of the digital economy. If AI growth accelerates faster than fabrication capacity, hardware constraints emerge. Not a collapse, but a bottleneck. Now consider water. High-density data centers generate significant heat. Cooling that heat requires either advanced air systems or water-based cooling solutions. Some large data centers consume millions of liters of water daily, depending on design and climate. In regions already facing water stress, this becomes a policy issue. Communities must balance industrial growth, residential consumption, agricultural needs, environmental sustainability. If AI infrastructure expands in drought-prone areas, trade-offs intensify. The AI boom is therefore not just a computing story. It is an energy waterland story. Then there is geography. AI infrastructure is not evenly distributed. It clusters where electricity is relatively affordable, land is available, regulatory environments are favorable, skilled labor exists, fiber connectivity is strong. This creates concentration. Concentration increases efficiency, but concentration also creates vulnerability. If too much AI compute capacity clusters in specific regions, local disruptions, weather events, grid instability, regulatory changes, can have outsized global impact. This is similar to semiconductor concentration. Efficiency creates choke points. Now let's examine the timeline pressure. AI adoption is accelerating across finance, healthcare, defense, manufacturing, education, consumer services. Businesses are integrating AI systems into daily operations. That creates baseline demand, not just research demand. Inference workloads, the everyday use of AI models, require ongoing computing power. Unlike one-time training cycles, inference demand grows with user adoption. If millions of companies integrate AI services into operations, compute demand becomes continuous. This shifts AI from experimental to infrastructural. And infrastructure must be reliable, which means stable power, redundant networks, long-term contracts, scalable cooling. The question becomes, is AI infrastructure expanding in coordination with energy planning, or is it racing ahead? Some regions are responding proactively. Energy providers are signing long-term agreements with data center operators. Investments in renewable generation are accelerating to meet expected demand. In some cases, nuclear power is re-entering policy discussions as a stable baseload option for data-intensive industries. Transmission expansion is being reconsidered. Industrial policy is aligning semiconductor production with AI development goals. But these responses take time. Energy infrastructure typically operates on multi-year to multi-decade planning cycles. AI model development operates on annual cycles. That gap is significant. There is also the economic dimension. Electricity is a major operating cost for AI data centers. If power prices rise due to increased demand or grid constraints, AI service costs increase. If chip prices rise due to fabrication bottlenecks, model training becomes more expensive. If water access becomes restricted, cooling systems must shift to more costly alternatives. AI economics are tightly linked to infrastructure economics. The AI boom is not just about algorithms improving. It is about whether the physical layer underneath can scale affordably. If it cannot, growth slows. Not because innovation stops, but because cost curves change. Now consider the global balance of power. Countries investing in AI leadership must also invest in semiconductor capacity, reliable energy, grid expansion, high-speed connectivity, skilled labor. AI dominance may ultimately depend less on software talent alone and more on energy and industrial capacity. In previous eras, economic power was tied to coal, oil, steel, manufacturing. In the AI era, power may be tied to compute density, energy reliability, semiconductor fabrication, infrastructure resilience. This reframes the AI race. It is not only a competition of models, it is a competition of megawatts. What would an AI infrastructure crunch look like? It would not be a dramatic blackout. It would look like delays in model releases, rising AI service prices, slower enterprise adoption, data center construction bottlenecks, local grid stress events, political debates over energy allocation. It would be gradual, subtle, but real. And because AI is increasingly embedded in productivity tools, logistics optimization, fraud detection, and industrial automation, a slowdown in AI infrastructure scaling could ripple through economic growth projections. The deeper insight is this: digital revolutions are physical revolutions in disguise. The internet required fiber. Cloud computing required data centers. Semiconductors required fabrication plants. AI requires energy. We often talk about artificial intelligence as if it exists in the cloud. But the cloud is steel, copper, silicon, water, and land. The AI boom is testing whether the world's physical systems can evolve as quickly as its digital ambitions. If infrastructure scales successfully, AI becomes embedded into global productivity. If infrastructure lags, growth slows and competition intensifies. The next phase of the AI era will not be decided only by breakthroughs in machine learning. It will be decided by transformers, transmission lines, fabrication plants, and power purchase agreements. In other words, by infrastructure. What to watch next? Pay attention not just to new AI models, but to energy contracts, semiconductor expansion projects, and grid capacity upgrades. That is where the real limits or accelerations of AI power will emerge. If you want to understand the systems behind global change, subscribe to Systems Watch. Thank you for watching.